Oh, good morning, everyone. Can you all confirm if you're hearing me clearly?
Yes.
Okay. Thank you so much. Thank you for confirming that. I want to welcome you to my lecture today. Of course, this is another statistical machine learning class. We started this particular topic probably on Monday, and of course, we're going to continue from where we stop. So the title is actually test data and topical modules. This is going to be part two. We're going to be focusing on modules today. Okay, we're going to be, like I said, we're going to be focusing on modules. And of course, what I mean, I'm going to be focusing on topic modules. Okay, but how do we find ourselves here? I remember I introduced you to topic modeling. A topical modeling is actually a powerful tool for analyzing large volumes of text data in in business applications, in genes. It has a very wide range of applicability. Just wanted to know that. You know, some of you may be wondering, what is the significance of what we're doing right now? Why are we trying to learn topics from documents? I think before moving ahead today, I'll need to first give you the example in business world. Okay, in business world, okay, topic models help in organizing and categorizing feedback. You all know that businesses have a way of getting feedback from their customers, right? Okay, the feedback is going to come in terms of reviews, complaints, and reports. Okay, putting reviews into consideration, a topic of modeling, we group similar reviews, okay, or into terms such as customer service, pricing, or product quality. Because there's going to be a review on whether your service or whether your service of good quality, what about the price you place on your products and the quality of your products. I want to believe every businesses they actually get review from that. So the topic model we allow businesses to quickly identify common praise or criticism without manually reading each review. Let me tell you this. Whether they don't have time to read all reviews, imagine they get millions of reviews. They don't have that. They don't have that time to go through that one by one. They don't have that time to go over all the reviews, but it's their way. They can quickly identify what the common praise is, what the criticism is. That can actually be achieved using topic modeling. So the topic modeling will enable us, we project these reviews from the high dimensional space to lower dimensional space. So there's a lot of example, okay, but I'm gonna move right now. Okay, so let me tell you this. When it comes to uh, you know, uh, discovery, aiding topics in document, we got a lot of methods that we use. And I'm actually gonna go over the method that we have identified today. And of course, what I'm actually going to do, I'm actually going to tell you what is the benefit of a particular approach and what is the weakness. Okay, I want to start with this latent semantic analysis. The latent semantic analysis is actually a foundational approach in topic modeling. Okay, so we actually call that LSA, and of course, this uses what I call singular value decomposition (SVD) that you've done before. Okay, so what is gonna what's gonna happen here is that at the moment you've converted the textual information into numerical representation in terms of matrix, you're actually going to have a way of applying SVD. And don't forget, the SVD is actually going to decompose matrix into three. Take a look at that. Okay, U, D, and the transpose of V. Okay, now I'm going to say um, the very first, if you go back to the Y, the matrix itself, which is a matrix that represents the document and word, right? And that very matrix itself is actually M by N. Okay, it's an M by N matrix where M represent the numbers of unique word, and N is the numbers of documents. And of course, you're actually gonna have in the matrix, there's gonna be an entry, okay, that will represent the weight or the frequency of a particular word in a particular document. Now, let me tell you how singular value decomposition work. You know, give me 1 second. If you take a look at right now, you really understand that why, okay, is numerical representation, okay, of the document and word, right? Arranged in row and column. And after applying the SVD, okay, you're actually going to have three lower matrices. This very U here, okay, is going to be M by R, okay? It's going to be M by R. I'm talking about the dimension now, okay? The M by R, that matrix U is an orthogonal matrix. R is just the rank of the matrix. R is going to be the rank of the matrix, okay? And that very U, the columns of U, okay, the columns of matrix U are the left singular vectors, and that represent the word in the reduced semantic space. Okay, it's actually going to the column of U represent, okay, the words, okay, WORDS in the reduced semantic space. Now, what about D? Okay, so D is going to be a square matrix R by R. Okay, it's going to be a square matrix R by R. Okay, and that's going to be the diagonal matrix with a singular, values. Don't forget the singular values that you're going to have a sigma 1, right? You're going to have a sigma 2, where sigma 1 will be greater than sigma 2, okay? Will be greater than sigma 3, okay, all the way, okay, to sigma R, okay? So if you consider all of that, you're actually considering a full rank, but we're not going to consider a full rank. We're only going to focus on the K singular values, okay? So because the approach is just to reduce the dimensionality, so which means you know um some informations that are not really of significant, they're actually going to be eliminated. So I'm actually going to tell you the significance of matrix D. The significance of matrix D in SVD, okay, as regard to extracting words, extracting topics in topic modeling, okay, will actually give us the importance of the latent factors, the importance of the latent factors, okay? So that very D, which is R by R, is actually going to tell us how important are the latent factors. Now, I want to go to V now. Okay, the one with the transpose, right? I want to talk about this guy now. Okay, this guy is actually R by N. Okay, the dimension is R by N. Okay, and let me tell you this, the rows, the rows in that particular vector represent the documents in the reduced semantic space. Okay, you now understand what each of these actually stand for. But let me tell you this, we're not going to use the full rank R. We're only going to consider the rank K truncated version of the SVD. Okay, because don't forget, we actually want to project the matrix into lower dimensional space. Okay, and that is the reason why at the end of the day, we're only going to be focusing on the truncated version, the rank K. K is less than R. When it has a full rank, it's actually going to have a rank of R. But right now, we're only considering the lower. So it's going to be, our K, don't forget, it's less than R. The K is going to be less than R. Okay, now at the end of the day, okay, we actually are going to use the reduced representation that capture the most significant relationship between documents and words. Okay, while we're trying to filter out the noise. Okay, we're trying to filter out the noise. And that's why we're trying to retain it, the K truncated version. I just wanted to take note of that. Okay, now, let me tell you, uh, what is the significance of using SVD? Okay, why is SVD useful in latent semantic analysis? Number one, because it allows dimensionality reduction. Okay, it allows dimensionality reduction. I just told you right now. And of course, not only that, the SVD capture latent relationship between the document and words. Okay, capture relationship, the semantic relationship between the document and words. And not only that, it also enables us to have a noise reduction. Don't forget, when you use a truncated, the SVD, okay, the rank K truncated version of SVD, you are able to reduce noise. Okay, so which means, uh, uh, you know, uh, this helps us reducing noise by only focusing on the largest singular values. Okay, that is that. Now, let me tell you this. I'm actually going to go into challenges that we have with LSA. Okay, why do we need to consider another topic model? Okay, apart from LSA, apart from latent semantic analysis, because we got a lot of it comes with a lot of challenges. Let me tell you, the challenges number one that I'm going to talk about is the fact that it uses linear algebraic nature. Because, when you take a look at the SVD, SVD is a linear algebra approach. Okay, and there is no any probabilistic framework in that. I'm going to say that again. There's a difference between mathematics and statistics. Okay, the LSA use SVD. singular value decomposition in topic modeling, and that is a linear algebraic nature. It doesn't have probabilistic framework. So the LSA relies on singular value decomposition, which is purely a linear algebraic technique. A linear algebraic technique does not actually use probabilistic model to explain the data. So if it doesn't use a probabilistic approach to explain data, then it means there's not going to be any probabilistic interpretation. Okay, there's not going to be any probabilistic interpretation of topics that we want to extract or their relationship to documents and words. Okay, and let me also tell you one of the challenges with LSA: overfitting. Okay, overfitting. Okay, that's one of the challenges. Overfitting situation where the model performed greatly on training data, but it's actually going to perform poorly on unseen data. Okay, overfitting. So the LSA can actually overfit the data. Why? Why? Because it does not incorporate a mechanism to handle noise explicitly. Okay, such as using regularizations or priors. Okay, so it doesn't actually incorporate all of that, and that's why it could overfit. And let me also tell you this: there is possibility that you're going to have a negative or in a U in the lower matrix U and V. There's possibility of negative value. Okay, there's possibility that you have a negative here and you also have a negative here. There's possibility. Okay, and having a negative doesn't make sense. Having a negative is going to create a problem of interpretation. Okay, it will be difficult to interpret a negative value, whether as probabilities or as a semantic relationship. And that is the reason. Okay, and let me also tell you another limitation of LSA. Okay, no generalization for new documents. Imagine you have a new document coming in. Okay, so you cannot generalize in the SVD. Okay, so once the composition is already complete, new document cannot be incorporated into the model. So if you want to incorporate a new document into the model, you need to recompute the SVD. That means you have to recompute the SVD again. Okay, so what is the way out? You understand LSA now. Okay, I'm actually going to tell you the way out. Okay, the way out is to introduce a probabilistic approach into the framework. But before going into the probabilistic approach of the LSA, I need to also remind you of non-negative matrix factorization. I explained this in class the other time. Okay, the non-negative factorization will partition a good numbers of dictionary documents into two matrices, and let me tell you, the matrices W and H, we've done it in a way that you are never gonna have a chance of having negative in any of that. So there's gonna be the first one that we call the set of words found simultaneously in different texts. And of course, the other part of the lower matrix is actually gonna be the weight to reconstruct each document. So these are actually, each of them is non-negative, which is very good in topic modeling, okay, because the word counts cannot be negative, okay. Okay, now, but you know what? This is still a linear algebraic approach, okay. Can we have a way to incorporate probabilistic framework? Okay. Okay. And that's going to take us to probabilistic latent semantic analysis. If you take a look at the difference between the LSA and this new approach, is just this guy. In the LSA, don't forget, the conventional latent semantic analysis only use a linear algebraic approach of singular value decomposition. So there's no probabilistic relationship between document and word. Okay, so the challenges that we experience under the conventional latent semantic analysis can actually, be addressed, okay, using this, okay, using the incorporating probabilistic, framework, into um, the architecture of the LSA. Okay, so with this, we're actually going to have a probabilistic interpretation, okay? Because now let me now start with this approach. What do we mean by this approach? So this particular approach that we call the probabilistic LSA, okay, does not use SVD. Instead, okay, it's a generative probabilistic model. I'm going to say that again. A generative probabilistic model. The belief is that each document is represented as a mixture of topics. I'm going to say that again. Each document is represented as a mixture of latent topics. And each topic, on the other hand, is represented as a distribution over words. As a distribution over words is what I mean by words. Okay. Don't forget. Okay. We got some words from document, right? Don't forget that, right? So the probabilistic latent semantic analysis, okay, actually believe that each document in the corpus is represented as a mixture of latent topics. Why do you say latent topics? Because that's what we want to identify. Okay, we believe topics are hidden. We actually want to, identify them. And the belief is also that each topic is represented as a distribution over words. I just wanted to know that. So the probabilistic LSA, okay, will lead to more interpretable framework. Why is it going to lead to more interpretable framework? Because we now have a probabilistic beta. Okay, it's going to handle sparsity better. Okay, because of the fact I'm going to demonstrate that to you. And it has a generalization capability. You don't forget the other time the conventional LSA cannot be generalized over unseen documents. But this has a generalization capability. Okay. And let me also tell you that one of the advantage of this is that it handle what I call polysemy and synonyms. I'm going to write that out. Polysemies, words. Okay. I'm going to write that out. Polysemy. Okay, polysemy. Polysemy are actually words with different meanings. Okay, so what I'm trying to say is that uh, the PLSA handle polysemy and synonyms. Okay, and synonyms. I'm gonna write that out. And synonyms. Okay, so it will actually this ambiguate a polysemous word and capture the semantical similarity of synonyms, okay, that the other one may not be able to do. Now I'm going to walk you through that now. the probabilistic is coming in. Now, when probabilistic is coming in, I want to walk you through the approach right now. Okay, we're actually going to benefit from multinomial distribution. Don't forget, if we have two topics that we want to discover, that would have been binomial. But in most of the time, we actually want to cover more than two topics. We want to discover more than two topics. Because of that, the idea of multinomial distribution is going to use. Okay, can you confirm again? Is everyone still hearing me clearly? Is everyone still hearing me clearly?
Yep.
Thank you so much. Now, like I said, probabilistic approach is being incorporated into the conventional LSA, and the probabilistic approach will make use of probability distribution that we call multinomial. Now, because of that, don't forget multinomial, situation where there is a possibility you have it's a generalization of binomial distribution, and of course, you know, in end trials, okay, each trial could lead to one or one more than two possible outcome, okay, and we believe each outcome has a fixed probability, and that probability is independent of other trials. We have a particular trial is independent of the other one. So you will know the multinomial. Okay, the multinomial is having more than two categories. Event can occur. For binomial, event can, there are two possible outcome, but here there's more than two possible outcome because the numbers of topics we want to cover will be more than two. Now, because of that, I'm actually going to go into the probability mass function of a multinomial distribution. Okay, so this is the probability of observing a set of count x1 up to xv. If the x1 up to xv is a random variable, of course, theta1, theta2 up to theta v is the probability for each class. And the x1, x2, they are actually the number of successes in each class. Okay, so this is the multinomial distribution. That idea is what we want to bring into the LSA. Okay, for us to have a probabilistic interpretation between the document and word. Okay, so this is I present to you multinomial distribution. This guy is just trying to say if I had x1, okay, to x2, okay, all the way, to xn, okay, that's going to give me n, which is going to be the totality of the sample size, which is going to be the numbers of trials. And that is what we're doing the factorial here. And of course, the theta 1, theta 2, up to theta n, of course, the sum of that has to be equal to 1. And whenever we have a probability, like, structure like this, we can say X follow a multinomial distributions with the parameter n and theta. That's exactly what we mean. So this idea is going to be incorporated into LSA. Okay, so it has application in language modeling, and not only that, in the voting behavior analysis in political science. If you really, maybe, um, the percentage that vote in the United States that voted for Republican Party, the one that voted for Democrat, the one that voted for Independent, because we got the numbers of parties involved is more than two. The multinomial distribution cannot be used. What about genetic inheritance pattern in biology? Because the numbers of class is going to be more than two, the idea of multinomial can also be used. Somebody sent a shot. I'm starting the meter one. We take yeah, you need to put on your camera for those that are writing exam. You have to do that. Thank you. Even though I'm in a class, then you need to mute, but your camera has to be on. Thank you. Okay, now I'm actually so we are on probabilistic latent semantic analysis, and of course, like I said, we want to uncover key topics. Let me tell you this. You need to know ahead of time the number of topics you want to uncover. And that is similar to the number of clusters that we've done in clustering. You know ahead of time. If you want to do clustering, uh, we need to predetermine what the number of clusters is going to be. Okay, so that also need to be known ahead of time. And don't forget, the each topic K is assumed to follow multinomial probability distribution. Okay, the multinomial probability distribution, and that's going to be on V words. Okay, and that is denoted mathematically as that. And of course, we're trying to say non-negative, and the sum of that has to be equal to 1. Okay, I just wanted to take note of all of that. Right now, we're actually incorporating the multinomial into the structure, okay, into the LSA structure. So if we have a document D, okay, let's say we have a document D. So we believe a document D is associated with a non-negative vector theta. Okay, and where does the theta come from? Theta lies in the k-dimensional space. Don't forget, K is in numbers of topics. Okay, and of course, theta we cannot be negative. Okay, it cannot be negative. It's a probability value. Okay, it has to be greater or equal to 0, and sum of probability has to be equal to 1. That's exactly what I mean. Okay, in case there's any question, please make sure you ask. Okay, so because of that, I'm actually gonna say if we have a data generating process, for each document, don't forget, in each document, we actually want to bring out topics, right? Okay, now we generate the length, okay, the document length. Document length is going to be ND, okay, and for each document length, don't forget what make the length of the document is the words, okay, is the words. So what we're going to say right now is that we actually generating topic. Don't forget the topic. We want to generate k numbers of topic, and we're going to do that by sampling, believing that if we're able to sample from multinomial distribution, we'll be able to uncover the latent topics. That's exactly what I mean. So take a look at that now. Okay, particular topic will come from multinomial distribution. Okay, and word also going to come. W is word. Okay, word also going to come from multinomial distribution. Okay, take a look at the probability associated with word and take a look at that as well. Okay, the idea of multinomial distribution is being used. Now, I need you to pay attention now. I need you to pay. Let me confirm again. Can you confirm again? I want to confirm again. If are you still hearing me clearly? Is everyone still hearing me clearly?
Yep.
Okay, I want to interpret this. Okay, I want to interpret this guy now. When you take a look at this guy now, it's like we're using the idea of a graphical structure, right? You remember graphical model. Now, if you take a look at this particular uh, diagram, this diagram now represents the graphical model of a probabilistic latent semantic analysis, PLSA, okay, which is a statistical model used primarily for analyzing co-occurrence data, okay, like in the document and word analysis. I want to explain to you one by one what is D. D here is document is shaded because it is observed. Okay, we observe the document, right? And that's why it is shaded. This is observed. Okay, that's why it's shaded. You're gonna have the access to the document. Okay, so D represents a document in the corpus. Don't forget, I told you on Monday, a corpus is a collection of documents for analysis. Okay, and it's an observed variable. Okay, and that is shaded. Okay, now take a look at this guy now. W represent word. Okay, you know, word is also shaded, right? Why is it shaded? Because it's also observed variable. This is also observed. Okay, word is also observed. But I want you to take a look at the one in the middle. That is not shaded. That is a topic. We believe the topic is unobserved. Don't forget the topic is what we want to figure out. Topic, okay, that is unobserved. That is the reason why it is not shaded. I just wanted to take note of that. Topic is not shaded because it's unobserved. And that's what we want to figure out. But when you look at the hedge right now, okay, the edge from D to C, okay, actually indicates, okay, that, you know, um, topic distribution depends on the document. Look at that. You see the arrow? Topic depends on the document. The distribution of the topic depends on the document. If I want to write that the conditional probability out, it's actually going to be the probability of C given D. Does that make sense? Take a look at that. It's going to be a conditional probability. So which is actually telling us for each document, there is a specific probability distribution over topics. That's what I mean. I'm going to say that again. For each document, okay, for each document, there is a probability, there is a specific probability distribution over topics. That's what the arrow, I'm talking about this arrow now. That's what it means. Now, what about the arrow from topic to word? Okay, the conditional distribution that is going to come out is going to be the probability of W given C, right? That's also a conditional probability. What that means, that actually indicate that the word distribution depends on the topic. I'm going to say that again. The word distribution depends on the topic. That's what it means. Okay. And what about M? What is the meaning of this M? Okay. That very M, the older rectangle, the bigger rectangle, that very M actually shows the repetition over document M. It's like, oh, this is going to be repeated across all documents under investigation. I mean, I have M number of documents. That's what it means. And that process is going to be repeated across M number of documents. Okay, you say confirm again if everyone's still hearing me clearly.
Yep, I can hear.
Okay, thank you so much. Now, what about N? Okay, what about N? Okay, the N actually indicate the repetition over words. It's like you have N numbers of words, like N words. That's what it means, N words. And the repetition is going to take place over N numbers of words. Exactly what it means. Okay, is there anyone who doesn't understand this network that I just show you right now? Is there anyone? Okay, so this is a probabilistic interpretation. If you take a look at the probability of C given D, okay, so that actually mean, okay, for a given document, okay, a topic is chosen according to that. Okay, that is a topic distribution for that document. When you take a look at this, okay, when a word is chosen, I just want you to take a look at that. Okay, so I said the word distribution for the selected topic. That's what I'm okay. Now, gonna move right now since you understand all of that. Okay, so in the model fitting, we're gonna use EM algorithm. Okay, expectation maximization. Okay, and we're gonna have a reasonable interpretation this time around because of the fact that we're making use of probabilistic reasoning. Okay, so each document has its own preference of topic and each position is associated with a topic. Just wanted to take note of that. Okay, now I want to go into the disadvantages now of this. Okay, I actually want to talk about the disadvantage of PLSA, computational complexity. It can also overfit. Okay, I'm actually going to say that it can also overfit. And not only that, let me tell you this. Even though we know that the probabilistic latency metric analysis provided an improvement over the conventional LSA, but I'm actually going to say it also has its own issue. And that is exactly what I'm trying to talk about now. There's no well-defined generative model for new document. And of course, document and topics are not associated in the mechanism, right? Just show. And because of that, we actually going to consider a Brown new approach, okay? And that very Brown new approach is actually going to be called a latent declet allocation. Now, let me tell you the improve, what this guy is actually going to do because we got challenges with PLSA. The challenges with PLSA, number overfitting, no prior assumptions. There's no prior assumptions, okay? And because of that, um, we needed a Brown new approach. And that is the reason why we're actually going with the latent declared allocation. Okay. Now, in this, we're gonna have the advantages of this guy over the PLSA is that it will handle overfitting and it's going to incorporate regularization parameter. Okay, the regularization parameter will come in terms of a prior. It's actually going to come in terms of a prior. Okay, it's going to come in terms of a priors, which means the idea of Bayesian analysis. Has anybody heard about Bayesian analysis before? Has anybody heard about Bayesian analysis? So Bayesian analysis actually makes use of a prior information. So prior information is the probability of the state of nature before collection of data. Okay, so the challenges with the PLSA can actually be addressed by LADA. Okay, the ADA we handle overfitting, and of course, with a priors as a regularization. Okay, now I'm going to go into that. There's a lack of prior knowledge in the case of PLSA, and that's exactly. Now let me just tell you this. I'm going to go back and I wanted to see the reason why the PLSA is weak. You know, if you take a look at this guy, each document we have that distribution. Imagine you have so many documents, then the numbers of parameters will be huge. What about this? Okay, depending on the numbers of words that you have. So we need a regularization, okay, that will control the sparsity. We need a priors that will control the sparsity of this guy and the sparsity of this guy. Because of the fact that we have more of document, there's going to be more parameter space. If you have more of words, there's going to be more parameter space. And that is why we need a prior knowledge. We need, and that is what this approach is bringing in. Okay. So we actually so because of that, I'm actually introducing you to DLA. Okay, DLA is an advanced approach and it incorporates prior knowledge into the architecture. Let me tell you this. DLA is a Bayesian version of the PLSA. I just wanted to take note of that. Okay, we're actually going to save a lot of space. Okay, that's why I said here, take a look at that. It saved the numbers of parameters. So If you save the numbers of parameter, you're actually going to escape over parameterization, and that will avoid overfitting. Okay. And because that is going to do that by giving us the distributions of that. Okay. Now I need you to pay attention now. The way the prior is going to come, this is it. This is the distribution now. We're going to use that as a prior distribution. We're actually using the Dirichlet distribution as a prior distribution to the multinomial distribution. The multinomial distribution is a likelihood distribution. The Dirichlet distribution is a prior, and of course, that's going to help us out. Okay, that's actually going to help us out. And they call the parameter alpha is actually going to control sparsity. Okay, so I want to explain this to you one. Oh, this is the mean and the variance of the distribution. That is not important here. Okay, all these are not important here. But what is important now, I need you to pay attention. I want to explain this. I'm actually going to spend more than the class time in case you have time. If you have class, you can log out at 11 a.m. I'm still going to continue my recording. Okay, but I want to explain this right now. Okay, like I said, this approach is a Bayesian version of the PLSA. We need this approach to control over parameterization, and that is going to come in terms of a prior. We're going to have to prior parameters, alpha and beta. Okay, you confirm again if everyone's still hearing me clearly. Is everyone still hearing me clearly?
Yep.
Okay, thank you so much. Now I need you to pay attention right now. I actually want to explain this particular diagram. Okay, now the diagram illustrates the generative model of ADA. Okay, this is an ADA. Okay, and that popular model. Okay, in relation to the PLSA, I just wanted to see. Now, when you take a look at the diagram right now, we actually have what I call this guy. Take a look at this guy. The guy, okay, is a discrete probability distribution over words. You can see that little word, right? If you look at the arrow, okay, it's a discrete probability distribution over words. And we believe that that is going to be drawn from Dirichlet prior distribution. Okay. Now, if you and that's what we have here, take a look at this guy now. It's trying to say if I have k numbers of documents, okay, I have a case number of document, I have a phi k that follow that distribution with parameter beta, okay, and what I mean, our k here is the total numbers of topics. The beta as a parameter is called hyperparameter, and that hyperparameter controls the sparsity of word distribution. I'm going to say that again. That beta, that is an upper parameter, hyperparameter, control the sparsity, okay, of the word distribution. In the PLSA, we're not able to control the sparsity of the word distribution. That's what this guy is going to do here. Okay. Now, when I move to the document level now, okay, when I move to the document level, okay, this is guy, give me 1 second. Before going to the diagram, I actually want to explain this guy now. How many documents do we have? We got M, number of document. Don't forget D equal to D represent a particular document. Could be one document, two document, up to M, number of document. Okay, so what this guy is actually talking about. For each document, okay, D, a topic distribution, theta D, okay, a topic distribution, theta D, is drawn from the Dirichlet distribution. I'm going to say that again. For each document D, a topic distribution, theta D. No, theta D is a topic distribution. Okay, it's been drawn from Dirichlet distribution. Take a look at that. Okay. Now, uh, another thing I'm actually going to explain here is I need you to take a look at this guy here. Each position has a topic, right? Now, what that guy is talking about, a topic ZI, this, if a topic is let's say a particular topic, Z, maybe Z1 or Z2 or so on like that, that is being sampled from the um, document topic distribution. This is a document topic distribution now, multinomial distribution. So that particular one is being drawn from there. Okay? I just want you to take note of that. There is similarly a word. Don't forget W represent word, right? Okay. We are also trying to say, if you come down here, let me see. Okay. Let me go back. The WI is also being drawn from, it's being sampled from the corresponding topic word distribution. Okay. I just wanted to take note of that. Now I'm going to go back to the diagram right now. I want to talk about the graphical structure here, and I need you to pay attention to this. Okay, I need you to pay attention to this. Okay, let's start with the alpha. I want to start with this guy, alpha. Alpha is an upper parameter, hyper. I'm going to write it out. Hyper parameter, hyper. Okay, they, oh, go ahead. Go ahead. Somebody want to talk? I think somebody says something now. What is that?
Yes, can you please explain again, like what does theta D mean? And it's like for each document, the topic distribution is being drawn from what?
Okay, so let me see. Which one do you want me to explain? Let me see. Okay, so which of these? Which of these do you want me to explain? Which one?
Yeah, like the theta D. You said
Okay,
is to be drawn from something, but I didn't hear it clearly, like from something.
okay. So you're talking about this guy, right?
Uh, no, it's the theta D.
Oh, okay, okay. I got what you mean now. Give me 1 second. So you are obviously talking about this one, right?
Yes.
Okay. Now, what I'm trying to say, in a sense, is that for each document, D represent document, right? For each document, a topic distribution theta D, a topic distribution theta D is drawn from Dirichlet prior. This is a Dirichlet prior distribution. The Dirichlet prior, when I say Dirichlet, I mean, let me give you the word Dirichlet. This guy. Do you see this guy? Dirichlet. So from Dirichlet prior. And what is the parameter of that? Is alpha. Do you understand now?
So the Dirichlet distribution is the prior distribution, and the alpha is the hyperparameter.
Exactly. The Dirichlet prior is a prior distribution, and alpha is the hyperparameter. That makes sense.
Okay, yeah,
Now you understand now, right?
yeah. And what does the ZI mean?
Uh, you said what is it? DI means which
Oh,
DI? Oh,
ZI.
Z. Oh, okay. Okay, let me now come to ZI now. Okay. Now, by ZI, we are actually referring to topic. Topic. Now, let me do this. Do you see that here I said each position has a topic, right? Can you see that? So,
Yes.
so ZI is a topic ZI, a topic ZI. There's going to be so many topics, right? So a topic ZI is sampled from document topic distribution. So the document topic distribution now is multinomial distribution. Does that make sense?
Yes.
So don't forget the document topic distribution is multinomial. That's a likelihood, right? Have I answered your question? Have I answered your question?
Yes. So, what is the difference between ZI and WI? Like WI is the topic of words, and ZI is the topic of.
Yeah, ZI is a particular topic.
Okay.
Like Z1 now, maybe topic, the first topic, Z2, the second topic. So ZI is a particular topic that we actually want to draw from a distribution.
Okay. And the WI is the topic of words.
Exactly. WI, and that's actually represent what I call the observed word, the word that you observe. I told you the other time, we are observing word, we are observing document, but topic is unobserved. So the
Mhm.
topic that is unobserved is what we want to learn. We are now assuming we are drawing that from a multinomial distribution.
Okay. I think I got it. Thank you.
You're welcome. Now, I want to go back and explain the graphical model aspect. Please, I need you to pay attention. I want to start with the alpha because there are two parameters, alpha and beta. So I'm going to tell you the role of alpha and the role of beta, and I need you to pay attention right now. Alpha and betas are hyperparameters of a Dirichlet distribution. So, you know, the alpha is hyperparameter for the Dirichlet prior over document topic distribution. Why the beta is the hyperparameter for Dirichlet prior over topic word distribution. Let me tell you this. There is document topic distribution. There is topic word distribution. So when I'm talking about document word, okay, document, okay, let me just say document word distribution, the parameter for that is alpha. Okay, so when I talk about documents, sorry, document topics. Give me 1 second. So this is document topic distribution. Okay, we're gonna have document topic distribution. Okay, okay, and here we're gonna have topic word distribution, topic word distribution, topic word distribution. Now, there are going to be two distributions, and that's why you are having two parameters, alpha and beta. So I'm going to say that one more time. Alpha is an upper parameter for the Dirichlet prior over the document topic distributions. Why beta, okay, is also an hyperparameter for the Dirichlet prior over topic word distribution. And let me tell you this, the two are upper parameters. Now, let me now come to theta. I want to come to theta now. Don't forget, the theta depends. If you look at the arrow, the theta depend on the parameter alpha, okay? And this guy here, phi, they also depend on the parameter beta. Just wanted to take note of that. So what is theta now? Okay, the theta is a document-specific topic distribution. Okay, document, okay, okay, that is document, doc, okay, specific topic distribution. Okay, document specific, okay, document or specific topic distribution. Okay, I need you to take note of all of these. Document specific topic distribution. That is what this theta represent. It's a latent variable that is not observed. It's a latent, okay, variable, latent. I just wanted to know that. Okay, I just talking about theta right now. Okay, as I talk about Tira, I also want to talk about this guy. Phi. What does that represent? That's a topic specific word. Like if you're talking about topic, word distribution. Okay, topic, specific word. You can see that is why it's coming from beta, because beta is for topic word, and that is why this theta is coming from alpha, which is a parameter for document topic distribution. Take a look at that. Now let's talk about Z right now. Okay, Z is a topic arrangement. I'm going to tell you again. A topic arrangement for a specific token, and this is latent. Okay, like I said, it's a topic arrangement. Z. Okay, it's also latent, it's unobserved. Okay. Oh my God. If you take a look at all the node, the only one that is shaded is W because it's observed. That is word, right? We can see word in document. That is observed. That's why it's shaded. Take a look at that. The only observed node here is a word. Okay? This word here is observed. Don't forget. Every other one is unobserved variable. Take a look at that. Okay? Now that's exactly that explain all of that. And let me tell you this. If you look at the arrow from alpha to theta, it means theta depends on alpha. That's what it means. Theta depends on alpha. And that's why the parameter alpha is very crucial. Your theta, which represent the document specific topic, actually distribution depend on alpha. Okay. Now I need you to pay attention to this now. Z depend on theta. If you look at the arrow, Z depend on theta. What does that mean? Okay, that actually means topic for each token as sample from the document topic distribution. Topic for each token are sampled from document topic distribution. Finally, look at the last arrow. The last arrow is pointing from this Z to W. What does that mean? It means words are generated based on topic. I'm going to say that again. Words are generated based on topic. That's what it means. I'm going to say that again. Words are generated based on topic. Okay. You can see the arrow. I try to explain the arrow. Words are generated based on topic. Okay. And what about M? The M is trying to say the repetition is going to take place over the M numbers of documents. Okay, the repetition over M, the numbers of documents in the corpus. What about N? Okay, the repetition is going to take place over N, the numbers of words. The N numbers of words, the repetition is going to take place. What about K? What about K? Okay, repetition over K, the numbers of topics. Repetition over K, the numbers of topics. I'm going to say that again. Okay. Repetition over K, the numbers of topics. N, repetition over N, the numbers of words. M, repetition over M, the numbers of documents. That is the explanation about that. And I'm actually going to move. Now, if you take a look at this picture, it's talking about the comparison between the IDA and the LSA. Okay? The IDA and this is PLSA, right? And this is what I just explained right now in the IDA. Okay, I just explained this guy now. Okay, go ahead.
Excuse me, Professor. It's
Yeah,
already
go ahead.
13. Cause are you gonna make it longer, the class?
Yeah, that was what I said. I said you can, if you have another lecture, you can actually leave. This is being recorded. Does that
Okay.
make sense? Yeah. I
So it
know.
will be like an hour or more.
No. I'm only gonna have like 5 more minutes to go.
Okay, sounds good. Thank you.
You're welcome. So I'm gonna let me say 11:20. I'm actually gonna be done. Okay, so when you take a look at this diagram now, it's only comparing the PLSA with ADA. Okay, that is what the structure is talking about. Now, in the PLSA, you can see the D represent the document is observed, is shaded. Okay, C represent the topic. The latent topic is not shaded, is unobserved. And W represent the word, it's shaded, that is observed. And you can see the arrow. Okay, the arrow here is actually saying the document influences the topic, as you can see. And the arrow here indicates that a topic determines the word distribution, as you can see. And that happened over the M numbers of document and so on like that. Now, I think I've also in the and if you take a look at the PLSA, there is no prior. There's nothing like alpha, there's nothing like beta, there's nothing like theta, there's nothing like phi. Okay, so here there's no prior distribution. Okay, there's no prior distribution in the PLSA. Okay, so here, okay, each document has its own set of topic probability. The set of topic probability is actually the probability of C given D. Okay, and if there's so many document, there's going to be so many of that. Okay, for larger data set, you're actually going to have large numbers of parameters. Okay, and that could lead to overfitting. Okay, the numbers parameter will grow linearly with the numbers of documents, which is a limitation of PLSA. It cannot generalize to unseen document, okay, and it will overfit with the high number of parameters. But in the case of this guy, of course, all is going to be fine because we got alpha and beta that control the sparsity. Okay, like I said again, the alpha, okay, is a Dirichlet prior over the document topic distribution, the beta, the Dirichlet prior over the topic word distribution, the phi, the latent topic distribution for each document, okay, the theta, the latent topic distribution for each document, Z, latent document, then W word is the one observed. I think I've explained all of that before. I just wanted to see the connection between them. So there's a lot of, I think I've already given you the differences between that, okay. I think I provided arrow, let me see, I provided how to do that in R. Okay, so my TA is going to walk you through how to do ADA because the ADA is the superior is the superior of the topic modules. Okay, that's why we're going to be focusing on the IDA, okay, in the lab. So you can practice this in the lab, but my TA is going to walk you through that. These are the code. But before you do that, you can try all of these out. You know what I mean? It's how to do that in R. Okay, it's how to do that in R, like I said. Okay, I put a lot here. Okay, so before I go today, I think I'm gonna say we are done now. We're actually done with this. And don't forget, there's gonna be information about presentation. You know, we're gonna be having presentation. And in the revision week, the first day of the revision week, I'm actually because we still have one more topic to cover, and that can be done in one class, which is topic mining. Okay, we talk about graph, the use of graph in this particular area too. This way I'm actually gonna stop today. Is there any question before I go today? Okay, I actually wish you a successful Thanksgiving. Make sure you stay safe. I'm gonna see you on Monday in person in class. Okay, bye for now, everyone.